for this lecture, I've decided to write all the notes previously and highlight the things I think are important and talk you through them, okay? So please do follow along. You do not have this part in your notes, but there are a few things here I would like you to be aware of in terms of how we measure all the different gas laws. We did this last time. You can actually go back to your last packet, and you'll see diagrams similar to these diagrams in your notes, okay? The important thing here that I want to get at is what the control variable is in each of these situations. So for temperature, to control that for Boyle's law, the volume has to be changed very slowly for the temperature to remain constant, all right? For you to see that change in pressure. That's pretty much all that's happening here, okay? We change the volume by applying force on top of the piston, and this piston is cylinder assembly. The way that this is drawn, this right here, highlighted in blue, all right? This is just our piston, okay? And this is our cylinder, all right? And the piston just moves up and down in that cylinder, all right? And therefore the volume and pressure change inversely. So the next example for Charles' law, what we have to do is maintain constant pressure. In order to do that, we expose some liquid, all right, to atmospheric pressure, and we can change the temperature. We can heat up the gas that's inside right here, okay? So, add some heat into here, all right? And when we do that, we see the volume increase. When the volume increases, okay, it's going to push this level of mercury up right here, okay? But that's pretty much that one right there. It's, nothing too complicated. And then for constant volume, we have a rigid sphere, okay, in a case. And what we do is we can increase the temperature by adding heat. All right, when that happens, you see this pressure go up, and this is the pressure gauge right here, indicating that. All right, so those are the ways in which we can measure the three gas laws, and these are what the relationships all look like. Now, for this one, for pressure versus temperature, this is a special one. This is what we use to determine absolute zero. And actually, if we look at a graph, okay, make temperature in Celsius, okay, we'll see that all of the lines that we get end up hitting the y-axis at some point, okay, depending on what type of gas you have. But all those gases, okay, are going to end up intersecting back at this point, negative 273 Celsius, all right, and that's going to be our absolute zero. So if you had a graph of P versus T where temperatures in Kelvin, this is where we get the directly proportional relationship as the temperature starts at absolute zero. Again, absolute zero is a theoretical construct where all the kinetic energy of the system is zero, right? Okay, so let's see here. We did that equation of state last time as well. These are just some old notes I have. Yeah, we can move forward here. Some other examples we don't need to worry about. All right. Okay, so starting with thermodynamics, okay, it's the branch of physics, all right, where we're looking at transfers of energy, okay, and essentially what we're looking at is just how a system is going to interact with its surroundings. And what this means is that the system we're typically talking about is some sort of working fluid, okay, some substance. We're going to be dealing with ideal gases in this chapter, all right. So heating and cooling a gas, doing work on a gas doing work itself, okay? And so what happens is that this ideal gas is going to interact with its surroundings, which is typically going to be some sort of piston cylinder assembly for what we're dealing with here, okay? That's the simplest example that we start out with. So the state of the system, okay, is whatever set of values it has for P, V, N, and T, okay? These are our state variables, P, V, and T, all right? And what these variables can end up telling us, okay, are the following things. All right, we can know the internal energy of a substance, right? The total potential and kinetic energy of all the molecules in that substance. The variable symbol for this is going to be U, and the unit is going to be joules. All right. So that's the first big idea we have here. We identified in the previous chapter, all right, that with an ideal gas there is no potential energy, and that's going to be a very important piece of our derivation coming up here soon for the different cycles. Anyways, the work that a gas does, okay, what I want you to think of is the fact that we have this piston cylinder assembly, okay, and in order for this cylinder to be pushed up like this, okay, it needs to do work. In other words, the gas is going to have to apply a force, okay, over some displacement. This delta S is our displacement. In order to have done this, we need to have applied a force. So we're going to have done work, okay? And what ends up happening is that the gas in our piston cylinder assembly is what is going to do that work when the gas is cooling or heating up. It will often expand, and that's when the work's going to happen, okay? So, the last piece here, thermal energy, right? It's what we see as a transfer of energy between two substances by non-mechanical means. It's a lot there. But non-mechanical means that we're not moving the piston. That's, work is when you're actually moving an object. That's the mechanical means. For energy to transfer by non-mechanical means, we mean by conduction, convection, or radiation. Those are the three modes of heat transfer. All right? So, the three modes of heat transfer, hopefully you studied in your other your physical science classes and chemistry classes, all right? But the way you can think of this, okay, is conduction is going to be heat transfer with no transfer of the substance. Okay, we're just going to have molecules vibrating and bouncing into the molecules next to them, all right, and moving the heat on down that way. Convection is when you have heat transfer with transfer of the substance. In other words, you have a bulk movement, and typically this happens with fluids, okay? That's where we'll see this. In radiation, well, that's just electromagnetic radiation. All right? Nothing too exciting there. They're different in terms of what you should already know. So thermal energy is going to be given to us in Q, and the units are joules. Okay? So there are 4 ways in which we can change the internal energy of a system. We can heat it. We have our cylinder right here, all right, with the Bunsen burner underneath it, all right. Our delta Q, when we're heating, we'll say, for example, is positive 400 joules. That means the thermal energy in is positive 400 joules. The thermal energy out, all right, would be negative 400 joules. So what that's telling us is that if we were to quantify the thermal energy that's leaving the system, it's negative 400, which means that we have to think of it in the opposite direction, okay? We have to think of the energy transfer the other way. That's always what the negative sign does for us. It tells us the direction of energy transfer, whether it's in or out of the system. And so whenever we deal with delta Q, it's always energy added to the system, okay? For cooling, we're going to be removing thermal energy. Remember, it's the transfer of heat, okay? So we have to go from region of high temperature to lower temperature. So what we see is that heat transfer, all right, here's going into the system, here's leaving the system, okay? So delta Q is negative 400 joules, so the Q in is negative 400, that's the opposite way here. In other words, Q out is positive 400 joules, okay? Again, these are notations. You're going to see variables. People are sometimes going to talk about Q in or Q out, and you may end up with a negative, and you have to know that that means that the energy is going the other way. So if you have a negative for Q in, it means energy is leaving. It's Q out, actually. So the other 2 ways that internal energy of a system can change, here I'll show you the non-mechanical means. These are mechanical means, okay? So in other words, we are doing work, all right? So when we look at this, we have expansion of the gas, okay? It's going to move this piston up, all right? Work, just in general, when we say work, it's going to be equal to 100 joules. In other words, what that means is that the work done by the gas, okay, will be positive 100 joules. Or the work done on the gas is negative 100 joules, okay? And the reason why it's negative is because the gas is actually the thing doing the work, so it's the opposite direction we should be thinking of. Again, compression, now we're pushing this guy down, okay? We're doing work on the gas, all right? And so in order to compress it, we have to add energy to the system. The work is being done on the gas, increasing the energy of the gas. So we say the work here is negative 100 joules, okay? In other words, the work done by the gas is negative 100 joules because the direction of the work is actually being done on the gas, not by it, okay? So, what this means is that we have some designations that we go by when we deal with these three variables. These are our three main variables for thermodynamics. Delta Q is the thermal energy added to the system. In other words, the Q in. Okay? W, when we deal with all these cycles, is the work done by the system. Okay? So that would be the W by that I have written up here. And delta U is going to be the change in internal energy of the system. All right? And that's going to be, whatever process we follow here is going to end up being equal to our delta U. All right, so let's take a look at a few examples of this. All right? So to begin with, we have a sample of gas that's heated by a Bunsen burner, and we allow this to expand. So in other words, the gas will be doing some work. Okay? So if 400 joules of energy is added to this gas, okay, and the gas does 100 joules of work by expanding, what is the resulting change in the internal energy of the gas? Well, let's consider this here, okay? If the gas has energy added to it, and then energy leaves the gas because it does some work, all right, we have to find the difference between both of those, which is what this equation does for us right here. And we see that the total change in internal energy of the gas is equal to this value right here, positive 300 joules, all right? Hopefully that makes sense. I mean, it's just an energy balance, how much is leaving the gas by the work it does, how much is being added to it by the heating. Another example here, okay? So here, we're adding thermal energy to it, but this time, we're compressing it too at the same time, okay? So the way that you want to think of it, all right, since W, we said before, is the work done by the gas, is that we actually want to end up adding that. So we're still going to end up subtracting it here, okay? Because that's going to end up adding it for us since it's negative 100 joules. Remember, the designation is the work done by the gas here, okay? It's an odd way of thinking of it, but you're not used to it right now. But that's just the way that we designate it. It's easy. It's best to think of it that way when we deal with thermodynamic systems. So the total change in energy, okay, of this guy is going to be positive 500 joules. If we compare both these situations, that makes more sense, right? Here we have some energy leaving the system by the work the system does. Here, energy is being added to the system by work done on the gas, okay? So the total change in thermal energy should be more over here. It should be a change in internal energy. So what this leads us to, all right, is a really, really important formula, all right? This is the first law of thermodynamics, all right? And it tells us that the total change, okay, of internal energy will be equal to the thermal energy added minus the work done by the system, okay? Another way you can look at this, okay, is that the thermal energy transferred to a system from its surroundings is equal to the work done by the system plus the change in its internal energy. So that's the actual definition, way that we say it. And so therefore, this equation is how a reflection of that sentence. But the actual equation that we use is this one right here. And that to me, having that minus sign with that work reminds us of it being the work done by the system, that why we're subtracting it, okay? So I like to look at it in this way. This one that's been boxed in blue here, and that's the way you can normally see it. This first law is a statement of conservation of energy, okay? Cannot get more than you put in, okay? It's all got to go somewhere. We have to account for it in some way. All right. So that's the first law of thermodynamics, okay? Okay. A few examples here. Again, gas gains 1,500 joules, all right? That means we're heating it, so its delta Q is going to be positive, and it does 2,200 joules worth of work. So again, work is going to be positive as well here, since the gas is doing the work, right? We want to see the change in internal energy. We see it's negative 700 joules, so the internal energy of the gas decreases because of the work it did in its cycle, okay? For B, all right, again, same thing, just determining the sign, and now we're doing work on the gas, so we see that that work is negative, and when we substitute it into the first law equation, we see that the change in internal energy of the system is positive 3,700 joules. All right. So this leads us to our final point. All right. Internal energy of many substances, all right, is going to depend on the temperature and intermolecular bonds. What does this mean? Well, remember, temperature is related to kinetic energy. Intermolecular bonds is going to be related to the potential energy of the substance, okay? And so there are two types of energy throughout the entire world, pretty much. Every type of energy that you consider is either KE or PE in some sense. So, internal energy of ideal gas depends on only temperature, okay? Why? Because we ignore potential energy, okay? That's a big idea for an ideal gas. Remember, the kinetic theory of an ideal gas states that there are no intermolecular forces at work, so we must ignore them, all right? And intermolecular bonds, and you know what I'm going to say slash forces here, add that little piece. Okay. So, what we see, okay, is that because there is no potential energy, we only depend on temperature for the internal energy of substance. Therefore, U is directly proportional to T, okay? So, there we go. The other important thing to notice is that the internal energy of an ideal gas is path independent, okay? So, it doesn't matter what we do to that ideal gas, you know, when the energy is added or when it does work, all that matters is the difference in its states, okay? That's what that's telling us right there. So really quickly, okay, I want to point something out to you here. The average kinetic energy, this is what this equation is right here, okay? And what this is equal to is 3/2 K times T. And this comes from the Boltzmann distribution of the molecules in a system, okay? We're not going to get into this. I believe that there might be a bit of some note of it in your textbook, and Wikipedia has a great article on it as well. So K in this equation is the Boltzmann constant. What the Boltzmann constant is equal to is the universal gas constant divided by Avogadro's number. All right. This is something that arises again in different calculations for a concept known as entropy. All right. Something that we're not going to get into, but what is important is taking these definitions, and when we substitute that in here, okay, to our definition for internal energy, in other words, if we take the average kinetic energy and multiply it by the number of molecules in our system, that's equal to the total internal energy of our system, okay? And we just said here that the average kinetic energy of each molecule is 3/2 kT, multiply that times n, and we see something very, very interesting appear here. Remember that K is just equal to R over Avogadro's constant. Let me show you the substitution on another slide here. In other words, 3/2, what's the previous equation here? 3/2 N times K times T, okay? And we said that K is just equal to R all over N A, okay? So if we substitute K in here, right, we end up with this 3/2 N over NA times R times T. And what is N over NA? Well, that's the number of moles, right? Because 1 mole of molecules is Avogadro's number, and N is the total number of molecules, all right? And nRT, ooh, this is very interesting, isn't it? 3/2 times PV, okay? So that's where we get the previous slide from. So we end up with the total internal energy just being equal to 3/2 times PV, okay? Oh, looks like I actually did that over here. Interesting, okay. Anyways, so we end up with this good relationship to describe delta U, okay? And so delta U, the only thing we're going to say that changes is the temperature or the change in the product of pressure times volume, okay? That's going to be very, very important in some of our calculations that we do later on. So that is it for our introduction to thermodynamics, all right?